So, without further ado, welcome everyone. My name is Tom Olson. I work for ARM, and I am the chairman of the working group formerly known as GL Next, now known as Vulkan. Just a very quick reminder of how we got here. We've all known for a while that the GL franchise needed a bit of a reboot. For various reasons, that turned out to be hard to do. But this summer, June, July timeframe, the stars lined up. The need became glaringly obvious. We were able to get a critical mass of people committed to this project and get it started. And we went public with the goals of the project and the vision, what we were trying to accomplish at SIGGRAPH last year. So since that time, we've been working like crazy people, trying to make that vision a reality. We're not done. We don't have a spec for you. But we've made enormous progress. We're very proud of it, and we wanted to tell you about it now rather than wait until everything is completely cooked. So this is a game developer show, so it's appropriate. We have a bunch of distinguished developers to tell you about the API, the shading language, the tools, the key features, etc. And I'm going to mostly just turn it over to them and go away. I really just have one thing to say, but it's a very important thing, so I'm going to say it 3 times. That thing is thank you. A lot of incredibly talented people have worked incredibly hard to get us where we are. That work is ongoing and their commitment is unflagging. It's a real inspiration to work with them. I couldn't possibly thank them all individually, much as I'd like to, but I am going to thank I'm going to thank one corporate member who deserves special mention. When we started this project back in July, the first question we had to face was, how do we get started? Committees are really good at some things, but designing new stuff from scratch is not a strength of a committee. Khronos has only ever succeeded when we start with something pretty good and use the committee process to refine it. So we needed to get started. In the middle of that discussion, AMD walked into the room and said, you need a place to start? Here's the mantle specification. Do what you like with it, no strings attached. I can't tell you possibly how big a boost that gave to us in terms of letting us hit the ground running, in terms of giving us confidence that this goal was achievable. And so where we are today they deserve significant thanks for that leadership. So from the bottom of Vulkan's fiery heart, thank you, AMD. That's all I got to say. Please welcome Johan Andersson from Electronic Arts.
Hi, let's see if my voice can do this. Seems to be working reasonably well. Okay, so hi, my name is Johan Andersson, and I'm part of the Frostbite Energy team over at Electronic Arts, and I'm going to give you a brief introduction to Vulkan. So let me just arrange a little bit. So, but before that, let's talk a little bit about the state of the industry. I think we've finally reached a point, finally reached consensus in the industry now that the future is having low-level and explicit graphics APIs with really explicit control and management everywhere. And this consensus took a lot of time and a lot of hard work to build, but I'm really glad that we've gotten to this point. So now on the consoles, we've been using low-level graphics APIs for a long time, but this is on a single fixed platform. Then with Mantle and the work that a few of us did together with AMD on it, that sort of pioneered a model that showed that this is possible to do on PC as well. This coupled with that we in Frostbite, as well as Oxide and multiple other game engines, quickly added support for Mantle, and we shipped real full games such as Battlefield 4 really early on, proved that this model actually works in practice also, which is extremely important, and it does work really, really well. Then with Microsoft's development with the X12 and Apple's developments with Metal, I think that's further contributed both to this overall model and approach and to build this consensus further around the industry around explicit graphics APIs, which is great. Though we do live in a multi-platform and multi-vendor world, and this is a good thing in general, but we need a standard that can reach all of it. An API that can run well on all modern GPUs, including existing GPUs that users already have. And with modern, I sort of mean around OpenGL ES 3.1. That's our current definition of modern, at least. and an API that can be supported on all platforms, including both mobile and desktop architectures, as feature-wise they're not really that different anymore. And more of us developers are targeting both. We need an API and a standard that can work well with both. We also want a solution that we can develop and work on together, not something that is just only owned and controlled by a single vendor or platform holder. That makes it very difficult to widely collaborate on it and for it to run efficiently on all platforms. And as part of this, we'd also like having a potential explosion of even more platform and vendor-specific graphics APIs. There shouldn't really be a need for that if we have a really good standard. We want to avoid a lot of pain and redundant work for us developers having to implement tons of different rendering backends and for GPU vendors to implement tons of different drivers. But on the other hand, we do need a solution that is also extensible, so we can make sure that we can get the most out of all GPUs and all different platforms in this really wide ecosystem. And finally, and this is something that I and a lot of people in the industry have been wanting to have for a very, very long time, and that is having a single binary intermediate representation for our graphics and compute shaders. This is really important to be able to separate the front end so that the languages you author your shaders and programs in from the backends, which are specific to each GPU architecture or platform. And such a solution is something that only can sort of successfully be built as part of a wide standard and sort of unify around that. Which brings me to Vulkan. Vulkan is our new standard. It's based on, just as Tom mentioned, based on Mantle that AMD graciously shared with all of Khronos. So we've taken Mantle, and within Khronos, we've essentially gone through this a little bit of a hybrid development and standardization process where we've kept what worked, we've changed what didn't work in this new wider context, and we sort of added what was needed. And I believe this is the best possible starting point we could have had, though I am rather biased. So you can see Vulkan as essentially a multi-vendor and multi-platform open standard successor of Mantle, which is really quite awesome. Vulkan is based on the same great model of explicit control and has extremely low overhead. And we've designed it to run really efficiently on a wide set of GPUs from different vendors and on multiple platforms. And as part of this, Vulkan has some really powerful advanced concepts, such as using multiple hardware queues for asynchronous compute and DMA, as well as managing and transferring workloads across multiple individual GPUs explicitly. And for mobile, we have explicit control over tile-based renderers with load and store operations into fast tile memory and having a very clear separation of rendering passes, so drivers don't sort of have to do guessing work and try to analyze what's going on. It's very explicit upfront instead. And there are many more concepts and tech details around Vulkan, and some of it you'll hear from the other speakers in this talk. But with all of this added together, for us specifically at EA and with Frostbite, it will be a fairly easy transition for us to take our Mantle render that we've been building for quite some time and switch it over to use Vulkan instead, in order to reach many more users once Vulkan is fully available. And one of the key things I would like to highlight last about Vulkan also is it's really been and still is sort of this unprecedented collaborative and rapid development within Khronos. And I would like to say that this is sort of a new Khronos. This is the Khronos that contains all the major game engine developers, and you'll see many of them here, lots of individual software developers, and all of the GPU vendors, as well as many of the platform holders, all working together. It's a really excellent community. And with this, we're together building a really solid and powerful foundation for the industry going forward. So that's all from me, and then the next section is from Val.
Thank you. I'm Pierre-Loup. I work for Valve, and I'm just going to give you a high-level overview of what Vulkan is, because some of you might not be familiar with Mantle, and even the people who are might not be familiar with the parts we changed. So the soul of Vulkan, like the principal concepts, are, as Johan was stated, a brand new API. This is a reboot. It has no common foundation with OpenGL. It is built with multi-threading in mind, so all the workloads you have, can scale to as many CPU cores as you want them to be. It will work on every vendor, every platform. We have a lot of Khronos members that have committed to supporting it, which is pretty exciting. And it gives app developers greater control compared to more traditional APIs like the OpenGL model. So to achieve that and provide with better drivers, better driver quality, and very lean, drivers, there's going to be a little bit of a trade-off. There's more responsibility on the app side. There's a little bit less error validation in the driver. So, for example, it's perfectly possible for an entry point to crash if you pass it something wrong, or to have like some synchronization problems between access to common resources. But that is fine because we'll be providing a lot of tools and a lot of validation suites, and John will be talking about it in more detail later. So no need to be worried about that just yet. Like when you're developing your application, you're going to have a lot of tools. Some of them will be open source, some of them might not, provided by the vendors. But they will make sure that your app is coding to the standard and basically compliant. Once your app is there, you switch to the runtime profile that is extremely lean and is not going to blow up or do anything weird. No performance hitching, no runtime shader recompiles based on state, no error validation in the driver or like weird things that will add overhead. So we think this is pretty exciting because traditionally in OpenGL world, the various implementations can have really different perf characteristics or weird behaviors depending on which path you choose, because the OpenGL standard has grown so big over the past years that, well, there's just a lot of room for error, lots of crevices you can fall into when developing to OpenGL. So how does scheduling work in Vulkan work? Well, there's two main objects. The queues are physical objects that represent something on the GPU. So a queue is kind of like the base object where you send work to be processed on the GPU. And command buffers are more logical objects that you use to build that work and precompile that work that is going to be scheduled in a queue. So again, for those of you who are familiar with Mental, these are kind of the same core principles there. So you can build command buffers or many threads. So the way it happens, if you have like a scene traversal system or an engine that can dispatch self-contained pieces of work, you can send them to a thread pool and have them built into a Vulkan command buffer. What this does is all the state validation, shader optimization, anything that needs to happen ahead of time will happen on that thread. And once your command buffer is built, this is a real GPU object that can be consumed and scheduled on a queue. So the only thing you need to do at that point is submit it on whatever thread is talking to your queue. So the goal for that is basically to keep all the overhead away from your main thread or your main rendering thread that is talking to a queue. So shaders, as Johan said, like the industry has stated the need for a binary intermediate representation for a long time now. So Spir-V is a brand new binary shading language that is designed for both compute and graphics. It is, some optimizations already performed while you compile offline to Spir-V. You can have tools that will use, high-level shading languages such as GLSL or other languages and compile them offline to Spir-V and give them to the driver at runtime, where it converted into GPU code that the GPU can run. It is a little bit higher level than some alternatives, so some things like flow control are preserved, so you won't get a situation where your offline compiler maybe unrolled a bunch of loops and then the driver has to re-roll them or crazy things like that. But at the same time, it means that there's not going to be a full high-level language parser in every different implementation of Vulkan, which is very good news because we've had, weird experiences with that sort of stuff where some of the drivers, might have different ideas about how to parse GLSL than others and things like that. So we think this is really good. It means you can build shader authoring into your content system. So, like artists, maybe like if your shader system is modular and you're assembling shader bits at content authoring time, then all of that can be compiled into Spir-V at that time. You don't have to kind of stitch together pieces of GLSL as your game is running and loading streaming assets. So the full spec for Spir-V has been released this week as a companion to the OpenCL 2.1 standard. And along that, we partnered with Linergy to write a shader compiler that will take GLSL and write to Spir-V, which is available right now under open source and a permissive license. So I invite you guys to go, clone it, play with it, make sure your shaders are compiling, but also, send us pull requests or even build it into your engine. It's entirely free to use. It's a, BSD, MIT-like license that lets you do basically whatever you want with it. So if you have, a cool shading language you'd like to use instead of GLSL, or if you want to just have your engine directly generate Spir-V bytecode, you can go and integrate some of that code, all of it, do whatever you want with it. So Vulkan is already here, and we're going to show you today a demo, or actually two demos of Vulkan running real-world applications. And as Tom said, we only started working on this 8 months ago last summer. So how does it happen that we already have something up and running? Well, starting from Mental was a big help, but what we did is, again, in partnership with Linergy, we created a sample reference driver targeting Intel graphics, and we've been making it available to other Khronos members throughout the course of development. So other vendors and ourselves have been able to use that driver as the standard was being developed to bootstrap their content and target Vulkan even before it was already released. So this is pretty exciting because it means that our source2 engine already supports Vulkan today, and that's what we're going to show you later. The spec and drivers that you guys can consume are going to be coming later this year. But again, a turnaround of 1 year for something like that is extremely exciting, and we can't wait to, have it in your hands and see what you guys do with it. That sample implementation I was just talking about will be open sourced in the same fashion as that GLSL compiler the day the spec goes live. So other vendors, software vendors, will be able to run against it on Linux or other systems if we do support that. See exactly what the driver is doing from their entry points. Traditionally, developing against graphics API is kind of a black box experience, right? And you make an API call, something happens, you're not sure what. If it does what you want, that's fine. If it's slower than what you want, if there's inconsistent performance results, if it crashes, if you get corruption, well, you can reread the spec 50 times, but at the end of the day, you're going to, email dev support for whatever your preferred vendor is, and it's going to be in their hands. That's not really how we want to do things anymore. So using that driver, you'll be able to see exactly what's going on. And Vulkan will be, foundational to Steam machines and support across the board here, no matter what the vendor is. So this is pretty exciting. So we're going to show you what I was talking about now. So this is Dota 2, the Dota 2 game and content running on top of Source2, running on top of the Vulkan driver we were talking about just now. This is running on Intel graphics. Right now it is pretty GPU limited on this little Intel integrated graphics chip, but we're still able to drive some interesting battle scenes. So, we supercharged Dota a little bit and added lots of creeps and, made for an exciting whole battle. So here our scene traversal system is, carving up chunks of code and scheduling into a thread pool where they're built into command buffers on many different threads. So we're keeping all the cores in the system occupied. And then we're just scheduling it on the queue. Again, we're very GPU limited in the system, but you get the idea. This is a very preliminary implementation. The way, being able to show you that, 8 months after the fact is really exciting. There's still some bugs. We have a bug where heroes come on screen and we do a last-minute shader recompile because we forgot to do a pre-caching in our asset system, but we'll fix all of that. So just a quick glimpse, and we'll have another demo for you guys later. So this is running on Linux, again against the driver that will open source when the spec goes live. And now Dan Baker is going to take over and go in a lot more detail on the threading model. Thank you.
Hi guys. So, I didn't read that title. That's awesome. So, what I want to stress about Vulkan is born of a solution to problems we were facing, and increasingly so in the consumer space for making real products. So the first thing I want to show you is, people ask me all the time, okay, that's just some tech demo. Why would you ever want to do that in a game that's not realistic? And I want to show an actual game and how we can hit enormous numbers of draw calls doing something that the player wants to do. Let me see if I can remember how to work this Mac. Alt-Tab. What, Command-Tab? Wait, VLC. Okay. This is our latest game that we just announced yesterday. It is called Ashes of the Singularity. It is a massive RTS. And as you can see, when you zoom out on the screen, it gets a little small on this projector, that we can have enormous amounts of stuff on the screen. And this is only possible on next generation APIs. That one was running the Mantle version. And so that's sort of the motivation. That's the type of games we want to make, and it's the type of games we're really struggling with because of API issues. So this is the key observation for the threading model in Vulkan. If we can see, over the last 4 years, we've effectively hit a wall for how much faster we can make a single CPU. In some cases, we've even seen single CPU cores decrease in performance over having more cores. And this trend is just continuing to increase. And the other trend that's also a concern is that GPUs remain getting faster more quickly than CPUs are. So at this point, when we're getting the latest processor, we're getting most of the performance because more cores are being added. Now, this is the key point. Even if you're not CPU bound today, it takes a long time to write a game. It can take many years to write it. By the time, if you start right now, by the time you release, it's very likely that even if you're not CPU bound today, that you're going to be by the time you come out. The conclusion here is that software needs to scale across other cores. It's going to become more and more true as the years go by. We struggled a lot in Vulkan. You should see the email threads about exactly what the threading model is. And it turns out that there isn't enormous amounts of industry standardization on what's going on. So we're a little bit inventing some terms here. But the term we finally came up with is caller-side synchronization. And this is a direct opposite of what you call free threading. And in free threading, when you call the function, it can have locks on it. In caller-side synchronization, we're changing the responsibility for synchronization to the application. Now, this is sort of like Spider-Man here. With great power comes great responsibility. But if you take that responsibility, the performance gains, as I'm going to show you, are absolutely amazing. And I also say that the current APIs do a good job of working on another thread, but the problem that we're running into is if you actually want to use all the cores, it ends up being an actual net loss. So what does this mean in a more tangible setting? The best way to think about it physically is the calls are siloed. They don't impact each other, assuming that you don't do anything wrong on your side. And effectively, Vulkan is organized so that a function, by and large, is only going to modify the output, and I have a little star there I'll talk about in a second, and it's only going to read the input. And this is actually very important. There's not global side effects happening. And because this is occurring, you can call these on many threads at the same time, as long as you're not stomping on the various things that are quite obvious if you did it wrong from your standpoint. Now, we've talked about this before. There's a contract now between the driver and the application. I'm not going to do bad things, and you're not going to do bad things, and everyone's going to be happy. Now, but a lot of people say, well, gee, Dan, this will make it a lot harder to program. But the reality is that the current APIs, theoretically, you weren't supposed to be able to break them, whatever you did, but the reality was you could. And you had to do a lot of things on your side anyway. So the contract is just making that level explicit. So instead of working around odd issues in the driver, in fact, we're just making that explicit up a level. This is a diagram of how you would expect the application to run at a very high level. One thing you can think of it not just running in the command buffers themselves can run in parallel, but we're also directly exposing the fact that the GPU is running in parallel. This isn't exactly true in the current generation APIs. There's some indications through extensions that the GPU is running out of band, but one of the issues is that there was an attempt to hide the fact that the GPU is an asynchronous processor from the CPU. This is removed in Vulkan. It's completely exposed to you that the GPU is another processor that's running out of bound. And this is a diagram of how we actually work, and it's fairly straightforward. The application writes to one command buffer, the GPU consumes from another one, and then you flip. And the deletion queues are just a little bit of a diagram of how you have to think about deleting things. It's really important that if you delete something in previous APIs, one of the reasons there's a lot of overhead, there's a lot of tracking to make sure when you delete something, you can't actually delete it right away because the GPU might be using it. In Vulkan, that's your responsibility. You can't delete something while it's being used. And this is a diagram of how you would build your software so that wouldn't happen. And it's not very hard to do. You just have to think about it, how it works. And this is a very safe way of doing it. Okay. So this is yet another way, I keep harping on the same things of thinking about it. So you don't have to really, I'm not going to talk too much to this slide, but when we're reviewing this on YouTube when it shows up, you can read over this. One of the big things that we're trying to make sure is that not only is it safe to call on all these different threads if you do the synchronization on your side, there's an implicit understanding and a lot of design work in the API so that there's no requirement for the driver to have a lock on its side. And that's really important because if you call into a function from two threads, even if it's safe, if it's locking, then it's equivalent of only having one CPU. So in every case we're making the API such that when you call in from two different threads, there won't have to ever be a lock on the driver side. Now the exception that you may sometimes see a lock and a serialization point is on creation calls. Depending on an allocator, you may sometimes see that, but that's a rare case. And Vulkan moves most of that, the creations up front, specifically to avoid that in your heavy frame-to-frame commands. So one of the things that we were seeing that was very frustrating to us is this is the old way of doing things, be it GL or DirectX 11. And what we were seeing was, even if you were on, say, a 6-core machine, you could be running your job manager, and you're really efficient, you've got all these little jobs, you can use all the cores, but then because the driver is only on one core, it's Amdahl's law. It doesn't matter. You can't optimize anymore because that's what's holding you up. And the really unfortunate thing is even barring a high efficiency in the submission, you can never get faster than that single core for the submission. So it was really critical to us to be able to have an API where we could use all the cores simultaneously. And the really exciting thing is just how much scaling we can get. And I'll show you that in a second here. So I don't know if you can read this. It's a little bit hard. Oh, yeah, I can see that. This is my ghetto setup, and this is our game running, showing you on a Haswell EO, which has 16 threads. So I thought, let's take an extreme case, what we can see. And this is running on previous generation APIs. And if you're really clever, you can figure out which one. And what I want you to notice is we are pegged out here on the application. We're doing everything we can, and it's pretty obvious, and you can play the game here. Where are the driver cores? And there's actually ends up being two threads. There's a main thread and a driver thread in the background, and they're basically playing a game of ping pong. And the really interesting thing when we profile this is we can't even max those two threads out because there's all these OS level primitives of some sort going on that we don't have any control over that aren't even keeping these full. There's also this graph can be a little misleading. The way Windows accounts for time slices isn't completely accurate. But it's pretty evident that we're not scaling across the CPU cores. We have 16 threads, and we're not tapping the potential at all. I mean, the entire system utilization is only 17%. And in this example, when the game is running, we are completely CPU bound in the driver, and that's really unfortunate. So, like I said, lots and lots of space that we should be able to use. So this is the Vulkan model. And now there is no driver thread. This is a big difference. Before there was this driver thread running in the background that was doing work. And while this worked well, if you weren't using that core and you could get everything done on one thread, if you were ever in the situation where that wasn't the case, it was going to hold you up. So in the Vulkan API, again, this is up to the application, if you can now spread all that work across every available slot. So if you notice, and if you're looking what our new thread frame looks like, that there is no longer any dead space. The only time you're going to get dead space is basically there's nothing left for the CPU to do because you're ahead of the GPU, and that's exactly where you want to be. And we're using some industry standard terms. The sim jobs for us are the things that are producing GPU payloads. So we have to wait until the fence is cleared so we can write into the data, and otherwise those guys can process. But the important thing is that when we get to the end of the frame where we're building the command buffer, we don't have to wait. We can submit all the information. You can see that the present job is actually spanning across the other frame and immediately begin processing the next frame. And we have complete control over that. So we can fill any dead time and keep our CPU completely busy. So we've been doing some simulations, mocking up Mantle to look a little more like GL for Vulkan Next. I'm sorry, Vulkan Next. I just confused a whole bunch of terms. Vulkan. It's Vulkan, not GL Next, but it's been a few months where I have to say one and I'm thinking the other, and eventually that was going to happen. All right, so we did some prototyping to make it look a little more like Vulkan and simulate what would happen if an infinitely fast GPU. But one thing is these new threading models are so fast, the high-end CPUs, like you basically can't get to the point where you're CPU bound until the hardware vendors get their act together and give me a GPU that's like 10 times more powerful, which I'm waiting for. So we were able to simulate that, and what we do is we effectively do all the work. Instead of blocking on the GPU, just generate the next frame. And so on the CPU side, we're doing a full simulation of what it would be like if we had a fast GPU. And we got some really great data on this. And so this is our game now running on the same exact, and we didn't change. This is running a game. This is not a graphics demo. Let me stress this. This is the entire game running. Now, when you run, the only change we made was switching into this new mode on the threading for the graphics side. And now, all of a sudden, the graphics driver is not blocking us. And we can get 95%, up to 95% scaling on 16 threads. We think we can do a little better. We have to figure out what's going on with that last 5%. That last 5% is really hard to get, I just have to say. It's just really elusive. So as you can see, as the spread counts go higher and higher, this is going to become progressively more important that we can spread across all the available resources. And the important observation is that even your mobile phone, how many people have like 8-core mobile phones now? That's like the thing, isn't it? Like 8 cores. So even in the mobile space, you're getting 8 cores. So it's really important we spread across. And for battery life, it's a lot better to run 8 cores at a lower clock speed than 1 core at a really high clock speed. We can actually observe power efficiency gains, even on the PC, by spreading across more cores rather than turboing 1 core. It's very, very obvious to us. You can plug a little power meter into it. You can run one mode, you can run the other, and you can see it. Sort of curious. And then one of the things, kind of a thought, is that there's a lot of game types that have been limited by overhead problems in the API. So Vulkan's going to not just change the way we build games, it's actually going to change what consumers see. We're going to see classes of games. I have no idea what we're going to see yet, but I'm excited. All right, and I'll leave it to the next person.
All right, hello everyone. I'm Smedberg from Epic Games. I'm gonna quickly just go over the resource binding model in Vulkan. So when the binding model was designed, it had a specific goal in mind. There's all kinds of different hardware out there, and we want a binding model that would work efficiently on all the way from the one extreme end to the other extreme end, and any mix in between. So there's the traditional hardware that has fixed function hardware for resource binding to the new, very modern kind of bindless-like operation. So, but in general, binding is pretty simple. This is really the only thing you need to know. One slide. You access a resource in a shader through a descriptor. There's different kinds of descriptors, samplers, images, buffers. The descriptors, you don't manage them from the CPU side per descriptor from descriptor. You do them in one go in a descriptor set. So you set all those descriptors in that set in one call. The bindings in this set is described by a descriptor set layout. Then when you set these descriptors for a shader, you don't have to have just one single set of descriptors. You can have multiple of them. And this would be described in a layout chain for the pipeline state object. So to allocate descriptor sets, there is a concept of a pool, which is basically like a memory heap kind of thing. There are two ways to allocate descriptor sets. One way is basically kind of a ring buffer thing, where it's called a one-shot allocation model, where you allocate new descriptor sets until the pool is full, and then that you reset and clear that pool and start all over again. It's basically just, you don't do individual allocations or freeze, you just keep allocating and then clear all of them in one go. Or the other way is a dynamic allocation, where you can allocate and free a descriptor set on the fly in any order you want. Of course, then you have to expect that there will be some fragmentation issues, and that has to be dealt with. So Dan previously talked about the multi-threading, which is a key concept in Vulkan. You can update these descriptors on any thread. A common way of doing or handling these, we hope, is to pre-allocate descriptor sets ahead of time. Especially you have a common descriptor set layout that a lot of your shaders are using. You pre-allocate those sets, and then at runtime you just update the data for those descriptors in those sets. For updating descriptors, there's two ways to do that. You have the by copy, which is kind of like the traditional, you give a copy to the driver and it will schedule that to be updated synchronously with everything else in the command, or immediately. And then, of course, you have to do your synchronization yourself, make sure that you promise that this descriptor is not in use when you update it. So I mentioned that you could have multiple of these descriptor sets for a shader, and they're ordered in one sequence, in a list, kind of, based on the order of, or the frequency of the update. So if you see on the second paragraph here, you have two different descriptor set layout chains, layout X, layout Y, and layout Z, and the descriptor set layouts that are of the lowest frequency of change is first, and persistent. So between two draw calls, you only have to update the layout W. You see. Okay, so that was the main thing, how it works. Pretty straightforward, really. There are some extra features in the binding model that I'd like to point out. Well, one thing is that you can set. Normally, you just set a descriptor set for here's for the PSO, and here's the shader with all the different kinds of shader and shader stages. Some hardware handles that fine. Here's basically some uniforms, and just any shader can use it. Or other hardware may run faster if you're a little bit more explicit up front, telling which shader stage should have which descriptor set. And you can do that with basically just a bit mask flags. The second thing here is that instead of just changing a complete descriptor set, you can have it, different versions of it in one buffer, and then just change the offset, which could be a little bit quicker. And then as a third point, we'd like to point out that samplers and textures can be treated separately compared from OpenGL before. Or if you still would prefer to treat it the same way, where samplers and textures are combined, you can still do that if you want to, for whatever unknown reason. Also, you can specify immutable samplers directly in the set layout. It's basically like a constant. It becomes like a constant that doesn't have to be updated at runtime. All right, thank you.
I'm Aras from Unity, and yeah, I haven't seen this talk title before, but yeah, it's a good title. So I'm going to talk about shaders in Vulkan. Some of that has been already mentioned in the beginning of the talk. So basically, the summary is that, well, we have the bytecode for shaders now, and it's a good bytecode, and, well, that's it. The primary reason why the whole industry almost wanted the bytecode is that half of the world actually does not even use GLSL to write the shaders in. Because people are on consoles, or people are making games for this other API. And no one really wants to write the shaders twice and keep them in sync, so people then develop various cross-compilers to convert from HLSL to GLSL, or compile HLSL into HLSL bytecode, and then parse that bytecode and emit GLSL out of that, and all kinds of crazy stuff. Instead, if we could have just bytecode, we could write tools to produce that bytecode from any language imaginable. And that's a good thing to have. So it allows people who want to use GLSL to use that, people who want to use HLSL to use that, people who want to use metal shading language to use that, and so on and so forth. And even to invent maybe new, better shader languages because, well, it's easier now. The other primary reason is that previously every single driver contained the whole compiler stack, which is not a thing that everyone should be inventing over and over again. And game developers typically lose countless hours and months and years on just fighting implementation details between these different compiler stacks. Both in terms of where compilers from different vendors have different bugs, and in terms of where compilers from different vendors have very different performance characteristics. So, for example, vendor A might load shaders really fast, whereas vendor B loads shaders on a similar hardware 10 times slower, and that's just a pain. Some people also have IP issues where they have significant portions of the code in shaders or in compute shaders, and shipping them as source code isn't really a good idea for their use case. So yeah, what Vulkan brings is bytecode called, or like intermediate language called Spir-V. Spir stands for Standard Portable Intermediate Representation, and it's supported both by Vulkan and by OpenCL 2.1. The Vulkan API consumes shaders only as Spir-V code or bytecode, and how do you actually produce that bytecode? It's up to you. You can use the reference GLSL to Spir-V compiler. You can use whatever you want. In OpenCL 2.1, Spir-V supports CL from the old versions of CL to the most recent version of CL. The other thing that was a key in specifying Spir-V was that to allow easy and lossless translation to and from other intermediate languages like LLVM, which is pretty much what everyone is using these days anyway. There's some differences in Spir-V between other commonly known binary shader formats like D3D. The differences is that there's no concept of a register pool, or the compiler doesn't have to try to pack everything into float force and to do register allocation. The compiler doesn't have to flatten all the data structures into just basically data that's just floats or integers. The type information is actually preserved. The flow control structures are preserved. So that actually allows expressing the actual intent of the shader instead of just getting a bunch of bytecode with floats in them in the end. Internally, everything is using single static assignment for all the intermediate results, which is a model that is pretty much agreed on to be a good model for expressing computation in intermediate languages. And load and store instructions are used for input and output from the shader, like reading the varyings and outputting colors and storing things into buffers and so on and so forth. The actual language is highly regular. It's like a stream of 4-byte words, and it's very easy to parse. So it's both fast to parse and easy to parse, and the driver part that loads Spir-V is actually fairly simple. What this allows is basically what majority of game developers wanted for a long time in OpenGL, is that we want to compile shaders offline. We want to do some optimizations offline. So basically all the front-end work can be done offline instead of game loading time. At loading time, there's still some work that needs to be done by the driver, because it needs to convert from this platform-independent representation into actual hardware instructions. It needs to do scheduling, it needs to do register allocation, all these things. So it doesn't magically solve the shader loading time problem. However, in Vulkan, because of more explicit nature, there's no hidden shader recompiles. You specify the full pipeline state up front, and that contains all the state that could possibly be needed to patch the shader. For example, some GPUs don't have fixed function blending at all, so they need to know the actual blending mode to insert blend instructions into the shader. Before, in pretty much all the APIs, that was done at runtime. Whenever you set a shader, draw something, change blending mode on some hardware, for example, you draw something else with the same shader, the driver would have to detect that something else has changed. I need to patch the shader, I need to recompile the shader, I need to redo all the scheduling work and so on. Another thing that Vulkan can do is it can basically save and load all these precompiled pipeline state objects. So in a sense, it's kind of similar to OpenGL binary shader caching. The difference is that it saves the whole pipeline object. So once you save it and you load it, then you know that it's never going to be recompiled at runtime in the future, which is a good thing. Oh, I actually already said that. So yeah, multiple source languages are possible. The other thing about Spir-V is that there's a core Spir-V spec which defines basic instructions that are in the intermediate representation, like how loads are done, how stores are done, and some sort of key operators. And the actual language-specific part is kind of separate. So, for example, the part that allows to use various GLSL built-in functions, for example, to compute cosines and do dot products and whatever, that's actually in a separate sort of subspec. And the part that allows to use OpenCL constructs is also kind of separated out. And in the actual shader, it specifies which of these possible extended instruction sets it's going to use. Yeah, then also a bunch of other sort of smaller stuff about Spir-V is that it's designed to be extensible, because, well, extensibility was one of the big things about OpenGL and is still a big thing about Vulkan. It allows to annotate various parts of the shader with debug information, so that various tools can be built to step through the shaders and debug them. And it easily allows various tools to just skip over parts of the shader that they don't understand. For example, if there's a tool that I don't know, that disassembles the shader, or if there's a tool for debugging and a shader is using some sort of extension that the tool doesn't know about, then the tool can gracefully skip over these unknown instructions, because all the instructions know their size, so it's easy to skip over them. And yeah, I guess I would like to sort of call to action in a sense that reference GLSL to Spir-V compiler is available now, spec for Spir-V is available now, and whoever wants to use different shading languages, well, you can do that now, and preferably release it on like GitHub and the open source license so that we as the whole industry benefit from that. So yeah, I'm gonna go back to John.
Hi, I'm John McDonald. I'm here from Valve, and I'm going to talk about how this is not going to be as terrifying as it just sounded. Also, I do have two tiny administrative things and then one apology. The administrative things are, please make sure you fill out your evaluations. I'm the last guy, so that I'll make sure that we do a better job as speakers in the future. And also, we've been told that I didn't think we were going to have time for questions because we had so much material. It turns out there's no one in the room after this, and GDC told us we can stay. So if you have questions, please stick around, and then there will be another opportunity for questions at other sessions as well. And then the apology, I will just apologize in advance if I start doing the baby sway. I find I just do it sort of subconsciously now to keep my kid happy, and so I may start doing it up here. I'll just apologize. So I want to talk basically about the fact that we've been talking for about 40 minutes now or 50 minutes now about how we're asking you to juggle chainsaws, but in exchange for juggling chainsaws, we're going to give you absolute peak performance, and you're going to be able to do things you haven't been able to do before. And it turns out that we've come up with a bunch of solutions to try and make this, a totally manageable problem and actually make your development very efficient. So one of the sort of new features with Vulkan that I think is pretty distinct from other things is the concept of the layered API, which we'll talk about in a minute. There's also, as compared to previous OpenGLs, there's an actual SDK that we'll be planning on delivering into your hands directly from Khronos. And then we have some other tools, and the cat's out of the bag, but we actually also have a perf demo that we're going to show at the end that totally came together at the last minute. So I'm super excited to get to show you guys that as well. So the layered API, basically Vulkan consists of multiple layers. They're at the sort of top is the application. It's sort of the topmost layer. And at the bottom is basically the driver. And in between these, there are basically these optional things. There's a loader, validation, there's ref counters, there's other official layers, there's things you write, there's things that you get from other vendors. The sort of salient point here is that you get to choose for the most part which layers are active, and it's a proportional taxation. If you disable a layer, it just doesn't exist. It costs you no resources, it costs you no runtime whatsoever, not even sort of missed jumps for function calls. So there are several sort of types of layers when we're talking about sort of to get a better idea of what these are. There's sort of application requested things like, hey, I want a debug layer or a validation layer, a performance layer, and we'll talk about what those actually are in a little bit. And then there's also sort of passive layers. These are things like the Steam overlay, because that matters to us, and fraps, which matters to them. But those are basically can be implemented as layers as well, which means that they're not doing really wonky behavior that maybe causes oddities in your application. There also layers can basically be open source, like all of the official layers that we distribute as part of the SDK are going to be BSD, MIT, permissive license. And proprietary layers as well. Rad Game Tools is already planning on a telemetry layer so that if you use telemetry, you'll just get basically information about your call usage right out of the box when you're profiling, which we're really excited about. So to switch gears and talk about the SDK that we're going to basically distribute, there's basically, like I said, there's an official SDK that has a BSD and MIT sort of open source license. You'll be able to get it directly from Khronos. And it'll, by the sort of current set of things that we think it will include are basically the loader library, header and build scripts per platform so that you're sort of, able to see what you're building against, and then the set of official layers as well, of course. And you might be saying, like, the loader? Why why are you shipping a loader? So obviously we do expect that platforms will ship a sort of default loader that you can absolutely choose to use. It should be on the platform and it should just work. But you can also basically ship a private version of the loader yourself as well. It's open source, and that sort of avoids the problem that maybe you're familiar with OpenGL32 DLL on Windows, and it's still OpenGL 1.1, and we're on 4.5 now, and that's a big gap. We don't want that problem to happen again, so we're going to make sure that you guys have loaders that you can use to basically locate the driver and find layers that are installed and get your app actually up and running on the GPUs in the system. Now, the layer is actually optional. So the loader, I'm sorry, is actually optional. It is just another layer. Don't go without it. That's a terrible idea. So this is sort of the set of official layers that we're sort of envisioning and actually working on right now to ship as part of the SDK. There's obviously the loader, which we've talked about. There's a validation layer, because as Pierre-Loup and others have talked about, there's not really runtime validation to speak of in the driver. Instead, we want to make sure that if you're generating a invalid command stream, that the driver doesn't need to worry about it. The validation layer will basically warn you, hey, this command stream is totally bogus. You're going to hang the GPU, or you're basically off in undefined territory. So the validation layer makes sure that you're not doing that. There's a reference counting layer to basically work with the problem that Dan Baker was talking about before, to help you make sure that you're not deleting stuff that's currently in flight. And that may also be useful if you're using some middleware that maybe is not quite as clever about their usage of the API as you are with your usage, because we're all super clever. It's definitely not our bug. There's a performance linting layer that we're talking about that basically looks for sort of common performance, idioms that are problematic in the API to try and warn you, like, hey, dude, don't do this. This is your hemorrhaging perf. You inserted a CPU-GPU sync point here. It just cost you 33 milliseconds. Don't do that. There's a debug layer, which is sort of separate from a validation layer. The debug layer is for when you're issuing a valid command stream, but you're getting the wrong picture, like you're not getting the picture you expect, and so it helps you do things like, I want to place breakpoints when the 37th object of this command buffer is executed, that sort of thing. There's a thread safety layer that basically is actually, that I'm working on, that actually is code gen from the same thing that we generate the documentation from, that makes sure that you are calling into functions in a thread safe way, and make sure, like, hey dude, you just did something, you totally are going to crash, and so you can enable this, and it'll help you track down any sort of threading issues where you're where maybe that one is your bug. Finally, there's a trace capture layer, which we have, which is already actually functioning, but I'm unfortunately not going to be able to show you today, which can take a trace capture of a live running Vulkan application at a very, very low overhead, sort of in the 2 to 3% area, and then a separate replayer that you can use to actually play it back, which, if you haven't done sort of tools work before, is sort of the foundation of tools work. Of course, this list could change, and if it does, you can bring pitchforks to my house, but you'll have to find it first. So the other things that the SDK will include are basically scripts to help you generate your own layers. These are the same scripts that we're using to generate layers, because code genning is awesome and powerful, and you don't want to repeat yourself 74 times. This is obviously helpful for you to track down application-specific bugs yourself, rather than having to modify your application to wrap every entry point. Instead, you could generate a layer and say, I think it's one of these entry points. These are the ones I want to pay attention to. Here's my app-specific debugging code, yada, yada. Obviously, we would also love for people to contribute layers back up if they find something that's really useful, because that makes all of our lives better, right? There's also the open source Intel driver, which will definitely ship at the same time as the SDK. It may not actually ship as part of the SDK. I'm not quite sure yet, but it's definitely going to be there, and it's the thing that we used in the Dota demo earlier today. And then finally, the GLSL to Spir-V. I'm the bad one. Bill was the old name. Yeah, okay, Bill was the old name, that's my fault. GLSL to Spir-V, sorry about that. And man, it had to be me, that sucks, okay. Finally, conformance testing is a big part of OpenGL. It's not, let's be honest, it hasn't been a large enough part of OpenGL. It's definitely a bigger part of Vulkan, and it's been very successful having an extensible conformance testing suite with WebGL. With Vulkan, we plan on open sourcing conformance testing as well. So you'll be able to download the same test suite that vendors run against their hardware to make sure that they're generating correct pictures on new hardware. And we'll totally accept patches for that as well. So if your application is doing something that you feel like is unusual, or hey, I found this implementation that's broken, if you want to strip it down and contribute a unit test back up to Khronos to make sure that your application continues to work, on future implementations of Vulkan, that's awesome. Patches are welcome, so please do. Finally, the last thing that I'm going to do before I do the performance demo is talk about some of the third-party tools that we've been working with. Lunargy and some folks at Valve have been working on Glaive, an open-source debugger for Vulkan. Now, if you're familiar with Voggle, you might be wondering, hey guys, you haven't had any updates on that in a while. And that's because we looked at it and we had support for GL3.3 compatibility in core, and we were like, we have finite resources, where are we going to spend them? We think it's more important to go ahead and have a debugger ready to go right away with the new API. So we've shifted gears and we've been building this debugger for Vulkan, which I'm not going to have time to talk about because we're going to talk about performance instead. But it's been developed in parallel with the API, and we expect it to ship at the same time as well. So finally, the last thing I'm going to do is we're going to talk about this performance demo. Awesome. Okay, so that's a pretty sweet background, man. I totally didn't notice that before. This is a demo. This came together from NVIDIA just basically yesterday. This may look sort of familiar. This is a CAD basically app. This is doing sort of hundreds of thousands of draw calls with several million triangles. And it's a little hard to see, but here at the top you can see in GL that this is doing a GL implementation right now. It's getting about 45 milliseconds per frame. And this is split in material groups. Now here, it was trying to do a good job of being clever about batching stuff together. Here, it's doing something that's sort of much more naive, and it winds up at about 145 milliseconds per frame. Now, when Piers goes ahead and adds this wireframe mode, this actually basically for each piece is drawing the object and then drawing the wireframe for that object and then drawing the object and drawing the wireframe. And obviously, there could be things that are cold here. There are not. Take my word for it. So now we're up to about 410 milliseconds a frame in traditional GL. And we can switch to Vulkan. And we drop down to about 90 milliseconds a frame, doing exactly the same workload as GL. We're pretty excited about this. There's been basically almost no optimization on the driver. Everything came together like last night at 8 o'clock. We're super excited that we got to talk about it at all, and that frankly, NVIDIA was able to bring us an awesome performance demo today. So big thanks to them for that. And I think that is everything. So, let's see here. Awesome. Okay, so we do actually have time for questions now. You can ask questions for all of us. Make sure you go to the mic in the middle, and let's get you guys back up here, and we'll pass around the little bonus mic, the speakers. And then if you don't get a question answered here, or whatever, you can also come to the SF Green Space. There are 2 sessions for Khronos today. This is the address. There's a session from noon to 1:30 where I believe there will be food, and then from 2 to 3 o'clock. And pretty much any technical question, totally fair game. So help yourself. Oh, and it's kind of a small room, so show up early.
There's a new talk, so we have time.
Okay. And I was just informed that there is actually a talk that's been added, and I got time for you too. So we'll bang this out pretty quick. I'm so sorry about that.
Are there any plans for console support, Orbis or Durango? Well, okay, Orbis or that other console?
Yeah, so the question is, are there plans for any console support? I can't comment on anybody else's plans, but outlook good? Let's go with that.
Well, I have almost a similar question. Can you say something about how this new API is going to be supported on existing hardware, and
So the
Platforms?
question, I think, is Vulkan going to be supported on existing hardware, or is it only...
Yeah, will 4.2 hardware support
So
Vulkan? And
when we were working on Vulkan, we decided very early in the process to limit Vulkan support to hardware that already exists and has existed for a while, because we didn't want to make an API that wasn't going to be relevant for 5 years while we're waiting for hardware to spin up. So what we did was we basically set the bar at ES3.1 and OpenGL 4.1, and hardware that supports that feature set will be able to run Vulkan. Now, whether you will definitely get drivers from the vendors definitely depends on putting pressure on the vendors, but we've gotten good sign-up so far. We're pretty happy with how the landscape looks so far.
okay.
Yeah, awesome. Thank you so much. And I think... I'm now told if we want to wrap up a little more, if you have other questions, we'll wander over to room 2003, which is down a little bit. You can come over and ask us questions, maybe in private if you don't want to, ask in front of a giant group. Thank you so much, everybody. We really appreciate it.